So good morning, students. So we completed with DC bridges, that is Wheatstone bridge and Maxwell Wheatstone bridge and Kelvin bridge. So there, Wheatstone bridge is used to measure the large amount of resistance in terms of kilo ohms. Kelvin bridge is used to measure the small amount of resistances for lead resistances and contact resistances in terms of like micro ohm or zero point zero 0.00 ohm. So we can use the Kelvin bridge. Those are DC bridges. So today I will teach you about the Maxwell's bridge. So this is a AC bridge. Maxwell's bridge is also called as a Maxwell's Vein bridge. So if you see this one, Maxwell's bridge is a AC bridge. It is used to measure. It is used to measure an unknown inductance in terms of known capacitance. So it is used to uh, uh, we can find out the unknown inductance by using the known capacitance. Okay, uh, so we can find out. This Maxwell's bridge is also a modification of Wheatstone bridge. It's a modification of Wheatstone bridge. It is used to measure the unknown inductance, uh, which is having low Q value. So the Q is nothing but quality factor, Q value, in terms of calibrated resistances. So that means we can find out the inductance or resistance and capacitance. So whatever the calibrated components are there, those are parallel resistor, capacitor. So whatever the calibrated components are there, those are the parallel combination of resistor and capacitor. So that's why we call this Maxwell bridge as a Maxwell's Vein bridge. It is named for James C. Maxwell, who described this Maxwell bridge during 1873. So he introduced this Maxwell bridge during 1873. Uh, so Maxwell's bridge, so if you see, it uses the principle that positive phase angle of inductive impedance can be compensated by the negative phase angle of capacitive impedance. So that means there are two impedances are there. So one is a inductive impedance. Inductive impedance means resistance in parallel with, sorry, resistance in series with inductance. There you have inductive impedance, and another one capacitance in parallel with resistor. So resistor is variable there, that is capacity impedance. So this will works on the principle of positive phase angle of inductive impedance, and where this inductive impedance is compensated by the negative phase angle of capacity impedance. When we keep this inductive impedance and capacity impedance opposite to each other, okay, so these two circuits are said to be in resonance. These circuits are said to be in resonance. So when the no potential difference across the detector, so that means when there is no current flowing in the galvanometer, uh, so when there is no potential difference, so there will be no current flowing in the galvanometer. So we can say that bridge is said to be in balanced condition. So we can find out the unknown inductance in terms of capacitance. So we can find out the unknown inductance in terms of when the bridge is said to be in balanced condition. So if you observe the Maxwell's bridge, so here, so these are the known resistances R2 and R4 are the known resistance. As I told you, so these capacitance and resistance are also known values. So that means here, this is inductive capacity impedance, and this is inductive impedance placed opposite to each other. Okay, placed opposite to each other. So these are the known values. So that means we know the capacitance value, we know the resistance value. You need to find out the inductance R3, inductance L3, and the resistance R3. Okay, you need to find out R3 and L3 in terms of known capacitance and resistances. So if you see the derivation in the balanced condition, so we know that Z1 Z3 equal to Z2 Z4. So if you see Z1, So let us consider this one is nothing but Z1. Okay, so this is Z2 and this is Z4 and this is nothing but Z3. So that means Z1, Z3 equal to Z2, Z4. This is the condition for balanced condition. That means when a bridge is said to be in balanced, we can say that the Z1, Z3 equal to Z2, Z4. So if you see Z1, so Z1 is nothing but R1 parallel combination with the XC1. XC1 is nothing but the reactance of the capacitance. So that means R1 parallel with JXC1. Uh, so you need to find out 1 by Z1. So 1 by Z1 you are getting 1 by 1 by 1 by Z1 you are getting 1 by R1 minus 1 by JXC1. So you know that XC1 equal to 1 by J omega C1. So 1 by J omega C1 means you will get 1 by R1 plus J omega C1. So 1 by Z1 equal to 1 by R1 plus J omega C1. So if you take LCM, what you are getting? 1 plus J omega C1 R1 by R1. So this is which value? This is equal to what? 1 by Z1. But you need Z1. So Z1 equal to what? Reciprocal. So R1 by 1 plus J omega C1 R1. And next Z2 equal to what? R2. So see here, Z2 equal to R2. Okay, Z2 equal to R2 and Z4 equal to R4 and Z3 equal to what? R3 plus J omega L3. Why? Because here Z3 equal to here resistance R3 and L3 both are series. So that means R3 plus JXL3. So reactance of our inductance is J omega L3. So Z3 equal to R3 plus J omega L3. Under balanced condition, you know that Z1, Z3 equal to Z2, Z4. So what is Z1? This is Z1. Substitute this value. So substitute this value in this equation. So what you are getting? R1 by 1 plus J omega C1 R1 into Z3. So what is Z3? So Z3 is this one. So this one you substitute in this equation. So substitute here. So R3 plus J omega L3. So what is Z2? Z2 is R2. So Z2 is R2 and Z4 is R4. So Z4 is R4. Now what you should do? Cross multiply. So that means here 1 plus J omega C1 R1 is there, no? So this will go this side. So that means what you are getting parallelly you multiply R1 with this one. So R1 R3 R1 R3 plus J omega L3 R1 equal to R2 R4 into 1 plus J omega C1 R1. So next R1 R3 J omega L3 R1 equal to, you multiply this. So R1 R4 plus J omega C1 R1 R2 R4. Now we have to equate the real part, this one and imaginary part, this one and this one. So you have to equate. So R1 R3 equal to R2 R4. So from this you are getting R3 equal to what? R3 equal to R2 R4 by R1. Okay. So next imaginary part. So J omega L3 R1 equal to J omega C1 R1 R2 R4. This is imaginary part. So that means J get cancelled and next R1 get cancelled. So what you are getting anyway omega is cancelled. So L3 equal to what? L3 equal to C1 R2 R4. So this is the inductance. So that means we can find out the unknown resistance and known inductance in terms of the known resistance and the known capacitance. So here you got, so if you see the bridge circuit, so you got R3 in terms of R1. So that means R3, R2, R4 by R1. So the known resistance, these all are the known resistances. And you got the inductance as the known capacitance and known resistance. That L3 equal to what? C1 is already known. C1, R2, R4. So this is the unknown inductance. So by using this derivation, you can find out the unknown resistance and unknown inductance in terms of the known resistance and known capacitance by using the Maxwell's bridge. Okay. So advantages, capacitance uh, capacitance of a capacitor is influenced by less external feeds, and capacitor is small size and it is low cost. So we are using capacitor, no? So we are getting the inductance in terms of capacitor. So these are the advantages of Maxwell's Wien bridge. Some practical issues are there. So these practical issues are, uh, when two inductors are proportionally inadequate, so what happens? There will be rise in the mutual inductance. So when you keep two inductance side by side, inductance, there will be a chance of developing a mutual inductance. Okay, due to this one, there will be fluctuations. That means there will be fluctuations between the two coils. Okay, so this is one of the practical issues in the Wheatstone bridge. So to minimize this mutual inductance, what you should do? Uh, so we have to keep perpendicular, not parallelly. So or we can keep separately or far away from the practical. So suppose we keep the Maxwell's bridge. So nearby some inductance or some electric motors, inductive elements are there. So they can produce some mutual inductance. Okay, so that's why to minimize that mutual inductance, we need to keep separately, or we need to keep perpendicular to the this inductive component. Um, Similarly, nearby present electric motor is an inductive uh, component, inductive device. Chokes, transformers, okay, may induce mutual inductance in the circuit component. That means if you keep nearby, they can develop the mutual inductance. So in order to avoid that, you should keep either perpendicularly, or you should keep far away from the Maxwell's bridge. So this is one of the practical issue in the construction of bridge. So coming to the phasor diagram. So phasor diagram. So this is a phasor diagram of a Maxwell's bridge. So here what happens? So if you observe this one, so this is arm AB, AB, AC, BC, BD and CD. No. So here in arm AB, the elements R1 and C1 are parallel. So therefore, take the voltage VAB as a reference and draw the phasor diagram. So here you have to take this VAB as a reference. So you have to draw the phasor diagram. Okay. So now IC. What is IC? IC is nothing but the current in the capacitance. Okay, current in the capacitor. So IC leads VAB by 90 degrees. IR1 and VAB are in phase. So IR1 is in phase with VAB. So that means, see here. So IR1 is in phase with the VAB. So VAB is nothing but a potential across the terminal AB. IC1 is nothing but in phase of how much? 90 degrees. No? So IC leads VAB by 90 degrees. So here this one is IC. IC leads VAB. This will be VAB by 90 degrees. Uh, at balanced condition, VAB equal to what? VAC. As R2 is the element in arm AC, so IAC is in phase with VAC. So see here. Mm, so here, uh, so anyway, the element present across AC is nothing but the resistor. So IAC is the current through the resistor R2. R2. So this is in phase of VAB. So VAC. So here VAB you can call it. We can say that VAB. Why? Because if you observe this one, AC and BD. So both are resistors. So AB. So resistance across this terminal R1 and AC. Both are resistors. So that means this IR1 in phase with VAB. IR2 is in phase with IAC. And next, at balance the same, IAB flows through R3 in the arm BD. So voltage across LX leads the current through 90 degrees. So the current through RX and VRX are in phase. So if you see, so see here, so voltage in CD. So voltage in CD is nothing but it will be 90 degrees. So if you see voltage in CD is nothing but due to inductance, this will be leads by 90 degrees. So voltage across Lx leads the current through the 90 degrees. The current to the Rx is nothing but Vrx. So Vrx is in phase with the IRx. So if you see this one, so here this is in phase with IRx. And next you have to calculate the summation of the vectors. So total current, you can find out the vector summation of IAB and IAC. So here you are getting the total current. So this is the total current. So here this one is total current. So total current is the summation of what? VAB plus VAB plus IAB plus IAC. Sorry, IAB plus IAC. So total current is IAB. So this is IAB plus IAC. And next you need to find out the total summing voltage. So total summing voltage is VAB plus VBD. So total summing voltage, here you are getting the total summing voltage VAB. So VAB plus this is BD. This one is D. VBD. BD. VBD. So the total summation of this VAB plus VBD, you are getting V. Okay. So so this is how you can find out the phasor diagram for the Maxwell's bridge. So this is one example. So in the given Maxwell's bridge, he given R1 as 1 kilo and C1 is 0.5 microfarads, R2 is 600 ohms and R4 is 400 ohms. So I have to find out the unknown inductance and capacitance, inductance and resistance. Okay, so you know that under balanced condition you got this relation. So R1 R3 equal to R2 R4. So here R3 equal to R2 R4 by R1. So 600 into 400 divided by 1000, you are getting 240 ohms. And next you need to find out L3. L3 equal to what? C1 R2 R4. So what is C1? C1 is 0.5 microfarads. 0.5 into 0 10 power minus 6. Micro means 10 power minus 6 into 600 into 400. So you are getting 12 into 10 power minus 2. So that is 0.12 millihenry. So hence, so you got R3 as 240 ohms and L3 as 0.12 millihenry. So like this, you can find out the unknown resistance and unknown inductance in terms of known resistance and capacitance. So next problem, a Maxwell inductance bridge uses a standard capacitor C3 equal to 0.1 microfarads. Supply voltage is 100 hertz. Balance is achieved. R1 equal to 1.26 kilo ohm. R3 is 470 ohm. R4 is 500 ohm. So you need to calculate the inductance, resistance, and also Q factor, quality factor. You need to find out the quality factor. So you know LS equal to what? C3 R1 R4. So what is C3? 0.1 microfarads 1 into 1.26 kilo ohm into 500. So if you calculate this, what you are getting? You are getting 63 millihenry. Similarly, what is R2 or RS? You can say here LS and RS. LS is unknown inductance and RS is unknown resistance. RS equal to R1 R4 divided by R3. So 1.26 kilo ohm, that is R1, and R4 is 500 ohm divided by 470 ohm. So you are getting RS as 1.34 kilo ohm. And quality factor Q equal to omega LS by RS. So what is omega? 2 pi f. So 2 pi into what is the frequency? Frequency is 100 hertz. So 2 pi into 100 hertz into what is LS you got? So LS is 63 millihenry. 63 millihenry divided by 1.34 kilo ohm. So you are getting the quality factor as 0.3. This is the quality factor. So by using this, you can find out the unknown inductance, unknown resistance, and the quality factor.